we need to determine whether the subset of M and N is a subspace of M and N with the standard operations, and we need to justify our answer. The set of all n by n matrices whose entries sum to 0 is M and N. So given that the set of all n by n matrices whose entries sum to 0 is the subset of M and N, and an empty subset W of a vector space V is the subspace if it's closed under addition and scalar multiplication. So we will check these two standard operations. So that is if U and V in W, then U plus V needs to be in W. If A is any scalar, so this is the first one. The next one is that if A is any scalar, then AU also in W. So U is in W, A is scalar, then AU in W. And let W be the set of all n by n matrices whose entries sum to 0, as n by n 0 matrix whose entries sum to 0, thus W is not empty. Let A and B be two n by n matrices such that all entire sum end up to 0. So all entries of A, I, J, where I goes from I and J both go from 1 to n. Denote the entire entries of matrix A. So entries of A and Bij, where I and J again go from 1 to 0, from 1 to n, entries of B, entries of matrix B. Then the sum of Aij, where I and J go from 1 to n, equals 0. And the sum of Bij, where I and J go from 1 to n, also equals 0. In this case, let's consider the sum of entries in A plus B. So we get it. The sum of entries of A and B are the sum of Aij plus Bij, where I and J go from 1 to n. By using summation property, we get that it equals the sum of Aij, where I and J go from 1 to n, plus the sum of Bij, where I and J go from 1 to n. And it equals 0 plus 0, so it's 0. So this means that the sum of Aij plus Bij, where I and J go from 1 to n, equals 0. So all entries in A plus B has sum of 0, so A plus B lies in W. So A plus B is in W. So we have proven the first property. Now let's look at the second property. So now we will take any scalar number U. Let A be in W. So this was part 1. This is first property. This is second property. Now part 2. So U is a scalar number. Then A is in W. And in this case, the sum of entries of A, so the sum of Aij, where I and J go from 1 to n, equals 0. Now we have to show that UA is also in W. So we will take the sum of all entries in UA. Then the sum of entries in UA are U times Aij, the sum of U times Aij, where again I and J go from 1 to n. Using summation properties, this equals U times the sum of Aij, where I and J go from 1 to n. So since we know that this equals 0, then it equals u times 0, so it equals 0. So we have proven that the sum of all entries of UA matrix also equals 0. So that means that UA also lies in W. So that means that W, so we have proven that both of these properties work. So that means that W is a subspace of M and N. Is a subspace of M and N. And the set of all n by n matrices whose entries sum to 0 is a subspace of M and N.